So today is our class of electrostatics, formula and important points. The next important formula for us is formula number 11, which is Gauss's law, which you all know is very important even for your class 12 finals. So it says the total flux through a closed surface is equal to the charge enclosed by the surface divided by epsilon naught. In integral form, the same thing we can write it like this: closed integration of E dot ds is equal to Q by epsilon naught. Okay? Now what is the meaning of this formula? What is the meaning of Gauss's law? So let's discuss few important points there. So say we have a charge Q here. So there will be electric field all around it. Now if we enclose it in a spherical surface, then on this surface, see this is three-dimensional spherical surface. So at any point on this surface, if we take a small surface ds, okay, so at this point there will be electric field here. So that E dot ds, if we multiply it, dot product, okay, then with that quantity, if we add such all quantities for all ds at different places, what we will get is, we will get the total flux, that is the electric flux passing through this surface. So total electric flux crossing this surface is equal to closed integration of, this is a surface integration of E dot ds, and which is equal to the total charge Q enclosed by this surface divided by epsilon naught. Since this is vacuum here, we are treating it as vacuum here. This is Gauss's law. The point we should note here is that this surface need not be a spherical surface for this formula to be true. This surface can be of any shape. It can be a cuboid. It has to be three dimensions, so it can be a cuboid. It can be a parallelepiped. Okay? So whatever be the shape of the surface, even the surface can be like this, an arbitrary surface, in three dimension. Whatever be the shape of the surface, the total electric flux crossing this surface is given by this formula. Okay? So this is a very important formula for our theoretical work. This is a very important formula for our entrance questions. So the next formula is formula number 12, which is electric intensity due to a line charge. So if you have a line charge, that is, charge is there in a line. Okay, say a very thin conductor is there where there is charge on it. So we call it a line charge. Okay. So from here, so I should write it all this. From here at a distance of r, if we have to find the electric field, that electric field is, equation is lambda divided by twice pi epsilon naught into r. So this is electric field. So it is vector. So obviously electric field means electric field intensity. So electric field intensity at a point at a distance r from this infinite wire, which is charged, which has some charge on it, is given by this formula, where lambda is called linear charge density. It is called linear charge density. I think you know this. You must have learned it in the theory classes. Linear charge density means charge per unit length of this wire. Next comes formula number 13, which is electric intensity due to a plain sheet. So if the sheet is thin, then the formula is given by sigma by twice epsilon naught. Sigma is surface charge density. So this is for a thin sheet, and for a thick sheet the electric field is given by sigma by epsilon naught. Okay, so if we have a thin sheet which is charged, so there is charge on it, then at a distance r from here, so I should write it like this, at a distance r from here at this point, okay, this is perpendicular distance r, the electric field here is given by sigma by twice epsilon naught. Notice an important point here, I think you know this, which is the distance r is not there in the formula. That means the electric field does not depend on the distance of this point from the sheet. It is same, it is equal at a near point, at a far off point. When we first learn this, it seems illogical. How can the electric field be same whether it's near the sheet or it is away from the sheet? But it is true. Remember, this sheet that we have taken is an infinite charge sheet. For that condition, this formula is valid. And in some cases, this you should remember for doing entrance questions, if the sheet is finite but the point is near the sheet, then we use this formula. Then don't worry about the fact that this sheet is not infinite, this is finite. So how can we use this formula? And if the sheet is thick, in that case what happens? This formula becomes this. So this is double of this. Now say, for your class 12 board exam, derivation of this formula from Gauss's law, derivation of this formula from Gauss's law, or derivation of formula number 12 for a line charge from Gauss's law is important. The derivations are important. But for entrances, you have to memorize the formulas. The derivations are not important. But you have to remember the concept. You have to understand the concept that these two formulas do not depend on the distance r. But for a line charge, just check, r is there in the denominator. So for a line charge, electric field depends on the distance of the point. But here in these two formulas, it doesn't depend. Okay. And now there is a special situation. The situation is our formula number 14. This is a special situation. So instead of writing it in mathematically, it's much easier to remember it graphically. So if we have two sheets, thin sheets, which are charged, say one is positively charged, its surface charge density is plus sigma, another one is negatively charged, so its surface charge density is minus sigma. Numerically they are equal, but one is positive, one is negative. In this particular situation, what happens is the electric field in this region is 0. Electric field in this region means towards the right of this plate is 0, left of this plate is 0, in between the electric field is given by sigma by epsilon naught. See? The drawing is there in my online course. On this side, electric field is 0. On that side, electric field is again 0. In between the plates, the electric field is sigma by epsilon naught. To make it easier for you to remember this, just think why it is 0, why it is 0, why it is this. Very simple. See, for this sheet, if you take a point here, this is positively charged, so electric field will be along this direction for this ship. For this ship, this is negatively charged, so electric field will be along this direction because this is negative, right? Now, the magnitude of the electric field for this does not depend on the distance. So this point is nearer to this point is further away from this shape. The magnitudes will be the same. The magnitude will be sigma by twice epsilon naught. Right? One will be positive, one will be negative. So they will cancel out, so it becomes 0. Similarly, in this region, take any point. For this, electric field will be along this direction, positive, away from it. For the negatively charged, this will be along this direction, negative, so attracts. Now, the electric fields do not depend on the distance, so their magnitudes will be the same. Clear? So they will cancel out, so it becomes 0. Right? Take a point in the middle. Electric field due to this is along this direction, away from it. Electric field due to this sheet is again along this direction, towards it. So these two will add up. So what we will have here is, for this sheet it will be sigma by twice epsilon naught. For this it will again be sigma by twice epsilon naught. Directions are same, so we add them up. So it becomes sigma by epsilon naught. Simple, see? You just have to think about the magnitude of the electric fields and the directions and use the formula for thin sheet, which is formula number 13. See, the way I have explained it, you should understand that approach, because many students think that why should I understand the concepts here? I will simply memorize this is 0, this is 0, so here this is this much. But what happens is, when you have to answer a question in the entrance, you have to apply your concepts for that particular situation. And that particular situation may be similar to this region or maybe some other region. So you have to understand, so this problem is similar to that situation. In that situation, I use this approach to get this formula, that is this result. This formula means what? In the derivation, the result is the formula. But in the numerical problem, you use that approach to get the result, and that result will be one of the options. Understand? So derivation of these formulas are also important to solve some of the questions that come in entrance exams. Some students make this mistake. They think derivations are not needed because derivations are not asked. In class 12 they ask derive this formula, derive that formula, but in entrance they only give numerical problems. But the catch here is that to solve some of the numerical problems, the approach is same as the derivation. Understood? So let me repeat. To solve some of the questions of entrance exams, the approach is similar to some of the derivations that we learn in the theory or concept part of that chapter. Okay, so that's all for today. If you have understood everything what I have explained, very good. If you have 2-3 doubts here, go through the video once again to see if it gets clear. And if it is not clear, write in the comment. I will explain it again in another video. Or if you don't want to write in the comment, which is public, anyone can see it, you send an email to me in my email address. I will answer back through an email to you. Okay? You may be wondering, we are learning only the theory part. Sir hasn't taught us any numericals. So let me stress this point that to solve numericals of the entrance exam, your concepts have to be clear. You must be able to remember the formulas. Then you must be able to analyze the problem to determine which concept to be used, which formula to be used. So till today, I've covered 14 formulas and important points. So now it is the time to take up numerical problems. So in the next video that I upload, we will solve some numerical problems.